Hello, this is lecture number 6 of CAD NPTEL video series lectures. This is the first lecture in solid modeling. A little recollection before we start: the extended Jordan curves theorem. A simple, closed and orientable surface bounds a solid. We have seen in lecture 5 what orientable surfaces mean to us. In a sense, a simple closed orientable surface can be discretized into surface patches. In other words, the bounding surface can be divided into different surface patches. Each patch has curved boundaries, and each curve has endpoints. While representing any solid in a solid modeler, both geometric and connectivity information should be stored and retrieved at any time. So what I'll do is I'll try to peel off the banana very carefully. I'll carefully cut the top part of the banana and try to peel it off. I'll be very careful not to damage the top part. So I have peeled off the outer cover into 4 pieces. This is the crux. I'm going to be taking off the substance. I'm a little hungry, so I'm going to be eating something. So what I'll do now is I'll try to, so this is what I call the surface patches. They're like surface patches. 4 patches here. So what I'll try to do now is I'll try to build them up using a sellotape here. I'll try to stitch the common boundaries between 2 surface patches like this. I'm not sure how good I am at it, but I'll try my level best. I'm trying to give a very rough idea. Looks like I have succeeded. Now the common edge between the other 2 patches. I'm going to be reinforcing the stitch. Now things are going to be a little difficult, but I'll try my level best. I'm not trying to go for a perfect stitch here, but something that is just workable for me to demonstrate the idea. And now for the final common boundary. And now for the top portion. So remember what I have done. I've taken away the substance from the banana. I'm still eating, I'm still working on it. And I have tried my level best to stitch the common boundaries together. It's pretty much like 4 or 5 different surface patches stitched at the common boundary. This is like the bounding surface of a banana, which represents the solid. So this lecture is about representation of solids in any solid modeler. Before we start, let's first look at the concept of half spaces. Half spaces are unbounded geometric entities. This is a keyword that works against the concept, but nevertheless, we continue with understanding what half spaces mean to us. Half spaces divide the representation space or the Euclidean space E3 into 2 infinite portions. One portion is filled with material while the other is empty. Surfaces are all half space boundaries in a way. Half spaces can be treated as directed surfaces. The direction vector would point towards the material side, and that's the reason why. Let's consider a few examples. A half space H can be defined as a regular point set in the Euclidean space such that the point set P belongs to the Euclidean space and f of P is smaller than 0. F of P equals 0 defines the surface equation. For example, a planar half space H equals a set xyz so that all z values are smaller than 0. This example corresponds to the x-plane. It is a set of all points in the 4 lower quadrants of the Euclidean space for which all the z values or the z values are smaller than 0. Example 2, a cylindrical half space, a set of all points which lie within the cylinder defined by the equation x squared plus y squared is smaller than the radius of the cylinder squared. A spherical half space, it's a point set of all points that lie within the spherical surface. A conical half space, again, a set of all points that lie within the cone. A toroidal half space, the radius, or rather the radii of the torus are R1 and R2. It's a set of all points that lie within the toroidal surface. How can solids be seen via the concept of half spaces? Complex objects can be modeled as half spaces combined using set operations. Set operations can be like union, subtraction, addition, or intersection. Half spaces that act as bounding patches for solids can be freeform surfaces. They need not all be analytical equations. Let's take an L bracket example with a cylindrical hole. Can we identify different half spaces? Let's see. The top face here is identified as H1. The side face as H2, the other side face as H3, the front plane as H4, this plane here as H5, the base of the bracket as H6, the back plane here as H7, and the top plane here as H8. The cylindrical surface is identified as a cylindrical half plane, H9. How can we think of constructing this L bracket using the concept of half planes? But first, let's imagine that all the directed surfaces are such that the material points into the solid. Let's try to construct this L bracket using the concept of half spaces. We can think of constructing this L bracket using a union of two blocks. One block would be this one. The second block would be this. Let's try to get the first block through different set operations operating on half spaces. The first block can be thought of being composed of the intersection between the half spaces H1, H2, the back side face H3, this front plane H4, the base plane H6, and the back plane H7. Likewise, the second block can be thought of being composed of the intersection between H4, this plane here, H8, which is the top plane here, H5, which is the front plane here, H2, the front side plane, H3, the back side plane, and H6, the base plane. H9, of course, would be the cylindrical surface. So the L bracket is a union of these two blocks, or an addition of these two blocks, and the cylindrical half plane subtracted from the result. A few disadvantages of this concept are that the half spaces can be unbounded, and these set operations would only implicitly store the topological and geometric description of a solid. Data storage would not be explicit. There are other alternative representation techniques which are used. We'll look at them. But first, what is expected from a representation scheme? For one, it should be versatile and should be capable of modeling any generic solid. One should remember the main classification theorem for surfaces here, that any solid can either be a sphere or a connected sum of different tori. a representation scheme should be able to generate valid solids. It should be complete in the sense that every valid representation produced is unambiguous. It should generate unique solids such that no two different representations should come up with the same object. It should encourage, or it should have closure rather, implying that permitted transformation operations, transformation set operations in particular, on valid solids always generates valid solids. Of foremost importance is compactness and efficiency in matters of data storage and retrieval. There are mainly two representation schemes: the wireframe approach and the boundary representation approach. The third one, constructive solid geometry, caters more to solid modeling. Both these representation schemes work well for polyhedral solids, and for all solids, non-polyhedral ones, that can be homeomorphically obtained from their corresponding polyhedral solids. First, the wireframe representation. This is one of the oldest methods to represent solids. As the name suggests, the representation is primarily through a set of key vertices connected by key edges. Remember, here we are not talking about faces, only vertices and edges. Both topological and some, and not all, geometric information is stored. As I mentioned before, faces are not considered in the wireframe representation. The edges may be straight or curved. A few examples here. A wireframe tetrahedron. You can mark or identify 4 vertices: vertex 1, 2, 3, and 4. You can also identify edges with numbers within parentheses. Edge 1, edge 2, edge 3, edge 4, edge 5, and edge 6. At this time, faces are not identified. One can come up with an edge table that records how edges are connected to different vertices. For example, edge 1 is connected to vertex 1 and 2. Edge 2 is connected to vertex 2 and 3. Edge 3 is connected to vertex 1 and 3. Edge 4 to vertices 1 and 4, and so on. This table here corresponds to the topological connectivity. How do we store geometric information? We use another table called the vertex table. The coordinates of each vertex are recorded in this table. Once again, we emphasize that we do not consider faces in the wireframe approach. Another example of a wireframe block. The edges are numbered within parentheses and the vertices are numbered without them. Like in the previous example, we'll have 2 tables: the edge table that would record the topological connectivity between different vertices and edges, and the other, the vertex table, that will record all the coordinates of all the vertices. First, the edge table that suggests that edge 1 is connected to vertices 1 and 2. Edge 2 is connected to vertices 2 and 3. Edge 4 is connected to vertices 1 and 4, and so on. And the vertex table that would record the x, y, and z coordinates of all the vertices or nodes. There are a few advantages and drawbacks of the wireframe approach. Wireframe models are very simple, but they are non-unique and ambiguous. This is because the models do not include the face information. Consider this wireframe model. One may not find it difficult to identify that the base is cylindrical, but one would find it hard to identify what is laid over it. Will this wireframe correspond to this solid, or will this wireframe correspond to this solid? It is not very clear. The second example, consider a block within a block. This represents a through hole in a block. What is not clear from this model is whether the opening of the hole is from left to right, like this, or whether it is from top to bottom, or whether it is from right to left. The boundary representation scheme takes care of the anomalies in the wireframe approach. This is called BREP for short. And the boundary representation scheme is an extension of the wireframe modeling to include the face information. Faces can either be analytical or freeform surfaces. BREP uses the concept from the extended Jordan-Scope theorem on boundary determinism, identical to what we discussed at the start of this lecture. To repeat, a closed, connected, orientable surface determines the interior of a solid. Both topological and geometric information is stored with the BREP approach. To emphasize, the face information is stored in particular. How do we orient faces with the BREP approach? Face orientations may be recorded such that the normal to the face points into the solid. This can be ensured by the clockwise ordering of vertices using the right-handed rule associated with the face. We'll consider a few examples in a few minutes. Using normal vectors, it is possible to distinguish the interior of the solid from its exterior. For example, consider this tetrahedron. The vertices are numbered as 1, 2, 3, and 4. The edges are numbered in parentheses as 1, 2, 3, 4, 5, and 6. Face 1 is composed of vertices 1, 4, and 2. Here, if we consider the clockwise orientation, you can imagine using your right hand and curling the fingers along this arrow with your thumb pointing outwards. If you think of that, you will notice that the thumb is pointing into the tetrahedron. Phase 2 likewise is composed of vertices 2, 4 and 3. 2, 4 and 3 would give you a clockwise order. Once again, if you use your right hand with your thumb pointing outwards, and if you curl the other 4 fingers along this arrow, you would notice that your thumb is pointing into the tetrahedron. How about phase 3? We have 2 choices here. Choice 1 is we can go back to face this plane here and order the vertices, or we can stand or sit right here as we are. Consider phase 3, 4, 1 to be the rear face and orient it counterclockwise like this. Once again, if you use your right hand, have your thumb pointing outwards, curl your fingers, you would notice that the thumb would be pointing into the tetrahedron. Likewise, the bottom face can also be ordered counterclockwise to have the thumb of your right hand pointing into the tetrahedron. This is an important concept in the BREP approach, the winged edge data structure. It is a data storage technique. It employs only edges to document the entire topology or connectivity in a polyhedral solid. Let's take an example of a tetrahedron, and in particular, let's consider edge 3. This edge connects two vertices, vertex 2 and vertex 4. On one of the sides, there is face A, and on the other side, there is face B. So edge 3 here connects vertex 2 with vertex 4, and on one of the sides, we have face A, and on the other side, we have face B. Recall the manner in which we had ordered the vertices for each face. For face A, we went clockwise. For face B, we went clockwise. With respect to the order, there will be an edge preceding edge 3 on face A, and there will be an edge that succeeds edge 3 on face A. In this figure, edge 5 would be the edge on face A that precedes edge 3, and edge 1 is the edge on face A that succeeds edge 3. Likewise, on face B, edge 2 precedes edge 3, edge 2 precedes edge 3, and edge 6 succeeds edge 3. Look at the structure here. It pretty much resembles a butterfly structure, with these extensions forming the wing of a butterfly. For which reason this data structure is called the winged edge data structure. Let's now see how the winged edge data structure works in case of a tetrahedron. These are the pictures from the previous slide. As I mentioned earlier, the winged edge structure uses edges as basis to record topological connectivity. In the first column, therefore, we have the edge number as the reference. For each edge, we'll have a start vertex and an end vertex. There will be two faces incident on the edge, face 1 and face 2. If you perform a clockwise traverse on face 1, what is the preceding edge, what is the succeeding edge, and likewise if you perform clockwise traverse on face 2, again what the preceding and succeeding edges are. We will record all these. Let us start with the first edge, edge 3. We know that the start and end vertices are 2 and 4. Face A and B are two faces incident on edge 3. For face A, the preceding edge is 5 and the succeeding edge is 1. For face B, the preceding edge is 2 and the succeeding edge is 6. Let us try now for edge 1. The start and end vertices will be 1 and 2. Once again, two faces are going to be incident on this edge, face A and face C. Face C is the bottom face for this tetrahedron. On face A, the edge that precedes edge 1 is 3. Note this clockwise orientation. Once again, the edge that precedes edge 1 is edge 3. The edge that succeeds edge 1 is edge 5. On the bottom face C, note this counterclockwise orientation because this is the rear face. The preceding edge is 4 and the succeeding edge is 2. Now for edge 2, the vertices are 2 and 3. Two faces incident on edge 2 are B and C respectively. On face B, if you again know the clockwise orientation, the preceding edge is 6 and the succeeding edge is 3. On face C, the bottom face, the preceding edge is 1 and the succeeding edge is 4. For edge 4 here, start and end vertices are 1 and 3. Two faces incident are D and C. C is the bottom face, D is the back face or the rear face. On D, the preceding edge is 5. Note this orientation here. For the face D, the preceding edge is 5 and the succeeding edge is 6. For face C, the preceding edge is 2 and the succeeding edge is 1. For edge 5, two vertices are 1 and 4. Two faces incident are D and A respectively. On face D, the preceding edge is 6, the succeeding edge is 4. On face A, the preceding edge is 1, the succeeding edge is 3. And for the last edge, which is edge 6, start and end vertices are 3 and 4. Two faces are B and D. On face B, the preceding edge is 3, succeeding edge is 2. On face D, the preceding edge is 4 and the succeeding edge is 5. So this table here, which is based on the winged edge data structure, stores pretty much the entire topological connectivity that includes the face information as well. What is left now is to store the geometry of the tetrahedron. We can use a few more tables for that. One would be the face table and the other would be the vertex table. The face table will contain information about the four faces A, B, C and D. We will note down the edges which are incident on these four faces, and we can use this table to also store geometric information for each face. We will have to use additional columns for that. In the vertex table, again we can store the four vertices, what edges are incident on each of them respectively. We can store the coordinates of vertices using additional columns which are not shown here. Therefore, we can actually store the geometry using additional tables. Note that these are non-unique tables. What I mean here is, if you look at the second column in both tables, the entries corresponding to the incident edges can be different. There may be other ways to construct the face and vertex tables. In real life, there can be many polyhedral solids that can have potholes and through holes. Let me sketch a figure on the board to show you this. Look at this figure, for example, a block with a pothole. This pothole is going to leave an internal loop on the top face of the block. How would the winged edge data structure work in case when these internal loops are present on faces? These are some candidate faces with a few internal loops. When internal loops are present, we assign them counterclockwise orientation, and we connect the internal loops with the external loop using auxiliary edges. In this figure, for example, these are the two auxiliary edges. Once again, the outer loop, the vertices on the outer loop are ordered clockwise, and the vertices in the internal loops are ordered counterclockwise. And we have used auxiliary edges to connect the internal loop with the external one. What happens in effect is that only one loop remains. Look at this figure, for instance. If I start traversing from this vertex clockwise, I go from here to here, then traverse towards the internal loop. I traverse the internal loop in the counterclockwise manner, go back to the external loop, traverse it clockwise, come back to the second internal loop, traverse it anticlockwise, once again go back to the external loop, and end up coming to the same vertex where I started. In the winged edge data structure, one should note that an auxiliary edge will have the same face on the left as well as on the right. In other words, it will be the same face as two faces which will be incident on the auxiliary edge. Euler-Poincaré formula. This is used to answer whether a polyhedral solid is a valid solid. The formula goes like V minus E plus F minus, within parenthesis, L minus F minus 2 times S minus G equals 0. I'll tell you what these alphabets mean. But first, let me say here that this relation is an extension of the Euler characteristic given by V minus E plus F. We will try to prove this relation later, or it can be given as an exercise to the students. Note that for a valid polyhedral solid, the relation holds true. However, the converse is not true. That is, if the relation holds true for any polyhedron, that may not be a valid solid. The Euler-Poincaré formula is extended to include potholes and through-holes. V is the number of vertices, E is the number of edges, F is the number of faces, G is the number of holes or genus penetrating the solid. It is the number of handles in case of connected sum of tori. S is the number of shells, and L is the total number of outer and inner loops. A little comment about the number of shells S. A shell can be identified as an internal void of a solid bounded by a closed connected surface that can have its own genus value. In a sense, whenever we see a closed, simple and orientable bounding surface, the shell value S is 1. We will take an example to elaborate a little more on the value S. Let's consider the first example. This is a cube or a block. The number of vertices, as we all know, is 8. The number of edges is 12. Number of faces, 6. Number of loops, 6. This is because with each face, a loop is associated. The number of shells will be 1 here because a cube will be a bounding surface comprising or including of 6 planar faces. It does not have a handle, for which reason the genus value is 0. If we plug in all these values in the Euler-Poincaré formula, we see that the right hand side turns out to be 0, suggesting that this cube is a valid solid. The second example. This is a cube with a pothole. Remember that the number of handles here will not be equal to 1, but will be equal to 0. Imagine that you have indented the pothole using a thumb on the outer face of the cube. The solid is still homeomorphic to a sphere. If we look at the number of vertices, it will be 16, 8 times 2. The number of edges will just be double of the number of edges in a cube, 24. The number of faces will be 11. This is because the top face here includes an internal loop. The number of loops will be 12. How? 6 loops corresponding to the outer cube and 6 loops corresponding to the pothole. The shell value is still 1 because we still have one bounding surface that we see, and the genus value is 0. If we plug in these values in the Euler-Poincaré formula, we again see that the right hand side is 0. The third example, a cube with a through hole. Now we have a handle. This solid is homeomorphic to a torus. We have an internal loop on the top surface of the outer cube, and we have an internal loop at the bottom surface of the outer cube. The number of vertices is 16, the number of edges is 24, the number of faces will be 10. Why? Because there will be 6 faces on the outer cube and 4 faces corresponding to the polyhedron inside it. The number of loops will still be 12. The shell value is 1 and the genus value is again 1. Remember that this solid is again homeomorphic to a torus. We plug in these values into the Euler-Poincaré relation and again see that the relation is satisfied. The fourth example, this looks a little complicated. We have a block within a cube and this is within the outer cube. What kind of a solid is this? Let me explain. The solid looks pretty much like this. Imagine that these two blocks have some thickness. If I insert a duster in one of these blocks, and if I try to cover the duster using the other block, this is pretty much how the solid in the slide looks. In other words, there will be material corresponding to the innermost block and its neighborhood is going to be void, and there will be material between the outermost block and the middle block. Is this a valid solid? I would say it is. Let's try to see what the Euler-Poincaré formula has to predict. The number of vertices, 24, the number of edges, they are 36, number of faces, they would be 16. Number of loops, they would be 18. What would be the shell value? Now, if you look at this polyhedral solid closely, there are two bounding surfaces. One that corresponds to the outer cube and the one that corresponds to the two inner blocks, which looks pretty much like a torus. So the S value for this figure will be 2. What is the genus value? Note that the bounding surface corresponding to the two inner blocks looks like a torus. It has a handle, so the genus value will be 1. If we look at the Euler-Poincaré formula and feed in all these values, we see that the relation holds. The right hand side of the formula turns out to be 0. Example 5. A cube with a dangling face. The total number of vertices for this figure is 10, 8 for the cube, 9 and 10. The total number of edges is 15, 12 for this block, 13, 14, 15. The number of faces is 7, 6 for the block and 1 dangling. The number of loops is also 7. And if we assume that this is a valid solid, the shell value, the number of shells, is 1 with no handles, and therefore the genus is 0. Euler-Poincaré formula predicts that this is a valid solid, but we know that this polyhedron violates the homogeneous three-dimensionality property of solids. This refers to the converse, that even if Euler-Poincaré formula is satisfied, the polyhedral solid need not be a valid solid. In this case, we see one face is dangling. Mr. Spock would want to ask now, what would be the different techniques for solid modeling? We'll cover them in the next lecture.